So well, if you want, you can go for lunch or rest a little bit. Just start the recording. Okay, so which problem was it? Problem 17. So you have, well, this practically is the same problem as 15. Part C or D, right? It's practically the same. It looks different, numbers are different, but it is the same story. Now, instead of magnetic field disappearing, you have the area disappearing. But it is the same effect. Well, let's see. Let's see what is happening here. So problem 17. Let me reduce a little bit the scale. Okay. So look, I can almost leave the solution, but okay, let's write it again because we're recording. So you have uniform magnetic field into the board, and use and the loop with given size. And they say that you change the shape from circular to practically a line in about in time interval that's given. Determine the induced EMF. Well, the induced EMF, V induced, again, is going to be in magnitude equal to, well, let's keep delta phi over delta t with minus sign. I'm just going to find the magnitude with absolute value. So this is going to be negative area of the loop times magnetic field. This is under the delta divided by delta t. The magnetic field doesn't change. It is constant, so you can get it out of the delta. And you're going to have the magnetic field out of the delta. You have delta area divided by delta t. And, well, the final area of this is not a loop anymore. The area becomes 0. So you have 0, the initial area, so final area is 0, initial area is pi r squared. And this is equal to B times pi r squared divided by the time interval that they give you, delta t. So that's it, right? It is the same problem. It looks different, but it is the same problem, like problem 15. Part C or D, whatever. So this is the induced EMF. The rate of heat generation. So this is A. The rate of heat generation, of course, is average rate of heat generation is going to be V induced squared divided by the resistance of this loop.
I think I was confused because I didn't know that the rate of heat generation was power. Right.
Average power. So rate means energy per unit time. Rate of power. Power is energy per unit time. Okay. So here energy is thermal energy. So that's. But this is the purpose of the practice test, which will discuss those terms. This terminology is used. Okay, so now the direction of the induced magnetic field generated by the induced current. So look, the original direction of the magnetic flux is into the board, because the magnetic field is into the board. You lose this flux. Lenz's rule says you have to compensate for this loss, and you compensate for that loss by having induced current in direction to compensate for the loss into the board direction, which means that you must have the induced current to be flowing in clockwise direction. Clockwise direction.
Can you just explain that one more time?
Yeah, you did.
So Lenz's rule says that you have to induce current in such direction that the magnetic field of that induced current to try to prevent the change of magnetic flux. So the magnetic flux was into the board and you lost it. You want to generate magnetic flux into the board to compensate for this loss. And this means that the current has to be flowing in clockwise.
Why was it lost though?
Because you lost the area.
Okay.
So why wouldn't the generated force be coming out of the board that to compensate?
Because you're losing.
It's trying to replace what it lost or it was originally. And it was going into the board originally, so it wants to do the same exact thing.
You want to keep it that way, yeah. Nature doesn't like changes.
Because you're losing it.
Yeah.
So if we were to expand the area, it would be opposite.
Yeah, yes. If this loop were elastic and you expand it, this means you're increasing the flux. You have to prevent this increase, which means that you have to induce current that is in counterclockwise direction.
So it's gonna be clockwise.
Yes, my answer is clockwise.
So the answer for this is clockwise. This is clockwise current.
Because it's asking about the direction of the magnetic field.
Oh, the direction of the magnetic field has to be into the page, but the direction of the current. So usually people ask what is the direction of the induced current. But this is easier question to answer. You lose the flux into the board, you have to create magnetic field into the board too.
X means into the page. And that means-
Okay, let's keep, yes,
Can we take a look at number 11, please?
problem number 11. Table shows the values of resistance, capacitive reactance, and inductive reactance for 5 circuits. Which circuit will give you a negative phase angle? So look, this is a little bit trigonometry. And trigonometry says that negative angles have negative tangents. So you have the tangent, so this is problem number 11. The tangent of the phase angle is XL minus XC divided by the resistance. Right? And well, you want negative angle. This means that you want negative tangent. And this means that you want the value of XC of the capacitive reactance to exceed the value of the inductive reactance. So let's see, where is the capacitive reactance larger than, so capacitive reactance larger than, it's the same. So only the last case, the capacitive reactance is larger. So only the last case, you have a negative phase angle.
And
Yeah.
Oh, okay, so just like remembering the phase angles, one of the tutors said like ice, like inductance leads voltage.
So in
That's something we should know. Or try to know.
So I don't know exactly this.
How do you know which one leads what? Like,
So in the case when you have larger capacitive reactance, the current leads the voltage. But again, I'm not going to ask about which one leads and which one. This negative sign means the current leads. Well, this negative algebraic sign means the current. So when the phase angle is negative, the current leads the voltage. But I didn't put any question about this in the practice test or in the homework assignment, so I'm not going to ask for who leads and who lags. In this class of this, everybody is a leader, nobody is a lagger. So this is enough to remember. Okay. Problem number 18. Problem number 18. So check the answers because some of the answers in the practice test may be wrong. So you have a generator with given RMS value and frequency. You're given the inductance of the inductor, capacitor, capacitance is given, and the resistance is also given. Part A, peak voltage from the generator. Remember always that peak voltage is RMS multiplied by square root of 2. And RMS is peak divided by square root of 2. So this much you have to remember. So in our case, it is the RMS is 180, the peak voltage is 180 multiplied by square root of 2. Okay, so capacitive reactance and inductive reactance. So capacitive reactance is 1 divided by 2 by frequency times the capacitance. Yes.
At resonant frequency, is the frequency equal to RMS value voltage?
No. So we probably have a question here somewhere about resonance. So let's keep going here. The inductive reactance is 2 pi frequency times inductance, right? Directly write those things. At resonance, you have resonance when this is equal to this. When capacitive is equal to inductive, you have resonance. Okay, so this is part A. Part B, find the impedance. Well, again, it is the impedance is square root of resistance squared plus XL minus XC squared, like this. Just a definition. what is the peak current through the resistor? What is the peak current through the resistor? Well, they ask about the current. So the peak current through the resistor is going to be, well, usually amplitudes we denote with subscript 0. So it's going to be the voltage subscript 0 divided by the impedance. Just Ohm's law, but instead of resistance, you have impedance. What is the peak current? So part G. What is the phase angle? Well, tangent of the phase angle is XL minus XC divided by R. Therefore, the phase angle itself is inverse tangent of XL minus XC over R. Average power supplied to this circuit. You can do it different ways, but you can say that it is average power. Well, you can write it in 4 different ways. Let me see how to write it for our situation. Well, write it probably like this is probably the easiest way to write it. It is RMS current squared multiplied by the resistance on, for example. And the RMS current is the amplitude divided by square root of 2. Right? RMS current is amplitude I note that you calculated in part C divided by square root of 2. So this should work. And you have 3 or 4 additional formulas to calculate exactly the same number. The number should be the same, no matter how you calculate it. Yes?
So will those average power equations be on our equation sheet?
Is it on the practice test?
No, there's just one power. There's 2 power.
Oh, there are 2 of them right here. Yeah.
Will we need to know all 4 then, or just those 2?
Well, those 2 would work, right? You have the angle calculated. You have, look, you have everything actually that is needed. But I have to add those if I forget.
So in
You have to ask.
E here, would we use Z instead of R on that?
Yeah, like I said.
No, here you only have resistance.
Okay.
But if one of the formulas in the list, for example, says that resistance is impedance times cosine here, right?
Yeah.
And if you replace that resistance here, you're going to get the formula that you have here. So you have infinitely many ways to. Yes.
Just to better understand resonance, like was asked before, would radio stations like radio, is that an example of resonance where XL?
Oh, absolutely. When you're tuning the radio, you're changing the resonant frequency of the RCL circuit of your radio to match the frequency of the station that you want to listen to. And that's it. That's as simple as this. And resonance in in technology and in science is the most sensitive way practically always to do things. So this is what you're doing. The entire radio, TV, cell phone, everything is related with resonance. So when somebody calls you on the cell phone, you get a signal. So different callers have different frequencies. So you slightly different frequency. So your phone receives a message. Tune to this frequency in order to listen to this phone call, and so on. And so everything is resonant frequency in RCL circuit, which practically not exists.
So for that example, are like cell phone towers just amplifiers?
The cell phone, so your phone is constantly in communication with the cell phone tower. Let's say every 10 seconds or so. I don't know exactly how often, but your phone, except if you remove the battery, and the new phones, you cannot even remove the battery. So you are constantly in communication with the closest several cell phone towers. And what was the question?
I was wondering if they're amplifiers.
Well, yes. So the cell phone tower receives your sound signal in particular frequency, and it is going to send it to other cell phone tower, and the other cell phone tower eventually is going to communicate with the cell phone of the person that you talk with. So it definitely amplifies your signal in order to send it to a cell phone tower that may be somewhere in New York. And then usually it sends it to first, to second, to third tower, but the distance between the towers is substantial, so you definitely have amplification. Yes.
So if you're close enough, you don't need service.
What do you mean? Close enough?
So since the power is amplifiers, you don't, if you're close enough to something, you don't need service to call it. It's still need the power, right? You pass it, but
So look, there is a modulation, and so when you talk, the cell phone, your cell phone is also modulating your voice. So you cannot, but yeah, if you're very close, actually. But it depends how the cell phone is programmed. And the cell phones are programmed to go to the tower rather than directly to your close cell phone that is involved. I bet that you probably can easily change the programming, and maybe people have done that. So you can use the cell phone as a workshop. You probably can do that, but it needs programming because the cell phone is programmed to communicate with the tower rather than directly with another cell phone. Okay, let's continue with questions and issues and comments and anything. Oh, problem making has more parts. So part E we did. Part F. What are the maximum voltages across the inductor, resistor, and capacitor? And look, the current in the RCL circuit is the same. The appropriate voltage across each of those elements is going to be according to Ohm's law. or modification of Ohm's law. So you're going to have like this. So the current you know already, right? Here is the current amplitude, here is the RMS current. They're asking about the amplitude. So the voltage amplitude through the resistor is going to be equal to the current amplitude that is here, multiplied by the resistance. The voltage amplitude through the capacitor is going to be the current amplitude multiplied by capacitive resistance. And the voltage amplitude through the inductor is going to be current multiplied by inductive. So inductor, resistor, and capacitor, they ask in this order. Yeah.
I have a completely different question, but I remember you talking about how, like when frequency goes to infinity or when frequency goes to zero, like capacitors will either turn to a wire or an air gap.
Yes.
And the same with inductors.
Yes.
Is there a way to remember, instead of just memorizing it, like is there a way to, like, frequency goes to infinity?
Here is how I remember it. When frequency becomes very large, 1 divided by very large number is small number, small resistance. What has small resistance? Wire. High frequency, well, low frequency, 1 divided by small number is a large number. Large resistance, air. Right? This is how is to remember things. In science and in physics, you don't need to remember too many things. You just have to remember how to think about that. Yes.
I don't know if anyone else had practice test questions, but I was hoping we could do just some of the quiz questions from slides.
Yeah, but you have to.
Unless someone else has practice.
Oh, but I have to send those slides.
Yeah.
I have to email those slides. Let me see if I can email those slides to everybody. Oh, I have to go to my office to do it. I cannot email the slides because they're in my desktop. But we can do other problems.
I actually have a question on a conceptual one.
Okay.
Can you help me with number 10?
From
The video, the practice.
the practice. Yeah, the term is.
Number 10, Mitchell, help me with that.
That will be great. Yes. So problem number 10 from the practice test. Which of the circuit arrangements will the power factor be non-zero? So power factor is defined as the cosine of the phase angle, and it is equal to resistance divided by impedance. So this is power factor. And once you know what the power factor is, so they say the power factor to be non-zero. So zero power factor you're going to have only if two of the, well, let's see it. We're going to make the general statement, but this is the way you can think about it. So this is resistance divided by square root of resistance squared plus XL minus XC squared. Okay, so knowing this, let's see. A capacitor in series with a generator. Well, if you have only a capacitor, this is not present. So this is 0, this is 0, this is 0. Well, 0 divided by something that is not 0 is going to give you 0, right?
Well, it has to have at least one resistor in it.
Yeah, well, or inductor, but let's keep going and we're going to see that. Only inductor. Again, no resistor. This goes away. And you have 0 divided by something that's not 0 is 0. Again, 0 power factor. Two capacitors. Well, two capacitors are as a single capacitor with effective capacitance equal to product divided by sum. So no difference it is just like case A. So it doesn't work either. D, a capacitor and resistor in series with a generator. So if you have a capacitor and resistor, you're going to have non-zero power factor, right? Because you're going to have only this is going to be 0, but you have something divided by something. It's not going to be 0. And again, E, if you have in E, you don't have resistor, again, 0 divided by something not 0 is 0. So only case D works. Only case D works. In other words, 0 power factor is going to happen always when you have 0 resistance. Well, with some exceptions that you don't need to. Figure 14. Okay, problem number 14.
It's just emotional, yeah, that's that, right?
I don't know what it is. Let's see. So you have rods with given parameters. It is sliding with constant speed. No other resistance. Magnetic field is given. Determine the speed of the rod. So the key here is that it is sliding with constant speed. So look, normally any object would be going down with 9.8 meters per second acceleration. Here, it doesn't, because the gravity force is exactly canceled by the electromagnetic force that acts on this rod. In other words, the magnetic force exactly cancels the gravity force. But you know that magnetic force that is acting on a moving rod in a situation like this is equal to what was it equal to? The length of the road multiplied by, well, here you don't have a current, so you have to induce this current. So it's probably multiplied by the induced current in this road, or current in this road, multiplied by the speed. And there is a factor cosine, which in this case is,
Instead of the speed, would it be magnetic field?
it will be magnetic field, yes. It will be magnetic field B. But the magnetic force is, yeah, the speed entered into the current, yes. Because the current is, it is there. So it's fine. And that should work this out. So
Now you can isolate finding current. Did you have it?
yes, and this is induced current, right? This is induced current. So from here, everything is known except the induced current, so you can figure it out. And therefore, once you have the induced current,
The speed defining.
V induced, yeah, V induced is going to be the induced current multiplied by resistance, which should be given, right?
Yeah.
And but on the other hand, V induced is equal in magnitude, no minus signs, of change of magnetic flux per unit time in magnitude, right? And this change of magnetic flux is, let's put the magnitude right here. So change of magnetic flux is going to be area times magnetic field divided by time. Magnetic field is constant. Write it like this. Area of this rectangular loop is going to be, so I have to introduce notations, but the area is going to be the length, so this length 1 meter, multiplied by this height h, call this height h, and all of this b, by delta t. And the length of the rod is constant, magnetic field is constant, so you can get them out of the delta, so you have L times B times the change of height. This is exactly the speed V, lowercase v. And this is pretty much it. So let's get the. So from here you have the speed V is equal, lowercase v, of course, is equal to the induced voltage in magnitude divided by the length and divided by the magnetic field B. And the induced voltage in magnitude is equal to current times resistance divided by LB. And Okay, so this is pretty much it. So this is equal to, so you're going to get some cancellations. So instead of induced current, say it is mg divided by LB. And after that, you have to multiply this by resistance and divide by L and divide by B. Well, you don't get any cancellations, but you get mg times resistance divided by L squared B squared. Well, this is what I get. And plug in the numbers and see if it is how. Let me see if there is easier way to handle this
I have a
problem.
question.
Yes.
So you gave us the equation that the induced voltage equals length times
Current times magnetic field. Yeah.
times velocity. Is that gonna be on the equation sheet, or are we gonna have to derive it like you did there? Because it's not on the equation sheet right now.
Which equation is missing? Say that equation.
Induced voltage equals length times magnetic field times velocity, which is what you got down there on the bottom. Basically just derived it, but you gave us that equation in class that you just wrote on the top.
Yeah.
So are you gonna give that to us on a test, or are we gonna have to derive it like you did on the?
So it is not in the
No, but you gave it when you lectured, you gave it to us.
well. If you need it, I'll put it in the formula sheet. Well, we actually had it in a different context. In class. Here it is okay. So if it is needed, I'll add it to the formula sheet. If I forget any formula, you have to ask and I'll write it on the board. Look, there are too many formulas and well, you have to pick and choose, and sometimes you have to remind me which formula is needed. Okay, we have time for one more question. One more question.
Another conceptual one, number 3.
So problem number 3 from the practice test. So you have a loop with given size and current in it is flowing. Uniform magnetic field in direction that is shown again in the diagram. What is the magnitude of the torque exerted so look, the torque is going to be 0 in this case. At this instant, when you have the orientation of the loop, the way it is, and you can figure it out the following way. So take some direction for the current, and this direction for the current is going to give you. So if current is flowing this way, the magnetic field of that current is going to be into the board. But this means that you're going to have North Pole behind the screen, South Pole in front of the screen, and it is not going to be anything related with so if you have a magnet, one magnet like this, oriented like this, and another magnet oriented like this, there is no interaction between them. So You just have to imagine two magnets that are oriented perpendicularly. In order to have interaction between them, you must have either north and north or north and south next to each other. In this case, any attraction is canceled out by repulsive forces. Is it the case or not? Yeah, it is.
So that's what I thought that it would be 0, but then in the answer key, it said that it wasn't. So that's why I got confused. with that.
It should be 0. It is probably a mistake,
Okay.
which means that, yeah.
Let me check.
So if it was perpendicular,
So you have to have it under some angle in order to have a non-zero force in the torque or a torque. So if it is under some angle, you're going to have, if it is
Isn't the
any
angle
angle.
90 though?
Say it again?
Isn't the angle 90 degrees?
It's the normal
Because
side.
the plane.
Yeah,
is
well,
parallel,
yes,
so-
you're right. So the angle has to be different, okay, than 90 degrees. You're right.
So then why, so does the torque equals current times area times magnetic field times sine of the angle not work then? Because it does give an answer.
Oh, you're right in this case.
the formula in the book
You're
says.
absolutely right, yes. So the torque is this. The torque is equal to magnetic field times the area of the whatever shape you have, times the current, times sine of the angle between this and this. Well, the perpendicular to that. And you're right. In this case, the torque is going to be just a product of those three variables. So I was wrong. So you have, the torque is going to be, they give you the radius, so you have to find you're right here. Not 0. Andrew, not 0.
Okay.
It is this.
Okay.
Yes.
On the equation, what is the equation in that
Which equation?
for torque?
For torque?
It has all of those and a capital N.
That's if it had-
Oh, if you have, instead of a single loop, if you have more terms.
And that's capital N turns per meter.
So capital N
So it's going
is
this way.
total number of turns. Lowercase n is turns per meter.
Is the normal?
How do we notice the angle is?
It is the angle between the magnetic field and the normal, the plane of the loop. The plane of the loop. So sine of 90 is 1. Yes.
I just have another question on wording. Like, so question 8, it says the current in the circuit reaches an equilibrium value.
You have a coil with resistance, self-inductance. Battery is connected. So once you turn on the battery, it is going to start increase. The current is gradually going to start increasing. Because the inductor is inducing opposite back EMF, back voltage. So it's going to be a slow process. But slow, it's not going to be instantaneous.
It's basically saying that the current isn't changing anymore. it's just constant.
Yes, exactly, yes. Okay, so let's end the problem solving right here. And in 2 minutes, I'll be back for the regular class at 1 o'clock. You can ask any questions that are related with the test.
So on that number 8, we just use the energy equation then.
So you probably, let's see, you're the inductance. So the energy stored, the energy stored should be equal to 1/2 inductance times current. That's correct. So probably stop this, or no, don't stop it. Let's continue directly. So we to have only 2 files rather than. Okay, so I'll be back in 2 minutes.
Yeah, I would.
I gotta go put the seat.
Like open the door.
Usually I swing the door open and people in there. So that, close my door real quick. Like 5 minutes till 11.
Yeah, she.
To work.
Is that the easiest way to do
Do you perchance have a key to the 130? I left my keys in there.
I have to access it from the hallway.
Oh, yeah, they were.
Is it new in there?
Yeah, they weren't done. Yeah. At least I saw that one. That's what he said.
Me neither.
Thank you. I probably just actually usually.
It was easier. I just don't remember his equation being on the. It was. Like, why did you not say?
The first equation.
Because you did that, you saw it first time.
I guess I didn't know.
Hold on, 'cause that one.
They do like take like 24 hours to go up like.
Oh, this is two, right?
That's not.
When he goes to the test.
Do you have a library?
Okay, so time to start the class again. And let's first try to answer the questions that you may have from chapters 21, 22, 23. Any questions from homework assignments or from the practice test or from any other source? So you two think about the questions that you may have, and let me show one practice test problem. So if you look at problem number 16 from the practice test. So this problem, I'm going to solve it, and people that want to have a version of the test with this particular problem have to tell me when I'm giving the test on Monday. It is test problems of your own choice. So, okay, so this is problem 16, I think, right? It was problem 16 that I promised you. So again, problem 16, you have to request a version of the test with this particular problem if you like. And here is what the problem says. You have a solenoid with given size and given number of turns. They tell you that this solenoid has current in it, and the current is changing at some rate that is given. And now inside the solenoid at the center, you have a conducting loop with given radius and oriented along the axis of the solenoid, the same direction as the axis of the solenoid. The first question is, find the magnetic flux through the small loop when the current in the large solenoid is 2.5 amperes. And this question is a direct application of the definition for flux. So the magnetic flux for any area is equal to the area multiplied by the magnetic field for this area, multiplied by the cosine of the angle between the normal to the area and the magnetic field vector. This is the definition for magnetic flux. So in our problem, here is the solenoid, and here is the loop inside the solenoid. Of course, you have some current right here. So we know that everywhere inside the solenoid, the magnetic field is magnetic permeability multiplied by the number of turns per unit length of the solenoid multiplied by the current. The current in part A is given. Lowercase n is the number of turns. For this problem, it is 1.5 times 10 to the 4th. 1.5 times 10 to the 4th. But unit length, and the length of the solenoid is 0.1. So this is the number of turns. Magnetic permeability is number fixed, constant, given. So area of the loop is pi times the radius of the loop, not the solenoid. So it is pi multiplied by the loop is with radius 0.02. 0.02 squared. So you have to plug in the numbers here. So this is part A. Practically part A is just substitution. The angle is 0. Cosine of 0 is 1, so you can skip cosine completely because it is equal to 1. So area is this, magnetic field is this. So part A is well known. Any remarks here? If not, part B, determine the mutual inductance of this combination, the combination of a solenoid and a loop inside. And to determine this, you need the definition for mutual inductance. So by definition, mutual inductance is the coefficient of proportionality between the magnetic flux in the secondary coil and the current in the primary coil. In this case, the primary coil is your solenoid. The secondary coil is your loop. So, by definition, the magnetic flux that we just calculated is equal to the current that is flowing in the solenoid multiplied by a coefficient of proportionality that we call coefficient of neutral inductance. Well, what was the answer that we got in part A? So if you substitute B with its equal and area with its equal, you're going to get area is pi r squared. The magnetic field is mu naught times n lowercase n times I. So that's it. Take this magnetic flux. You have pi r squared times mu naught times number of turns times current is equal to mutual inductance times current. You cancel the current and the coefficient of neutral inductance is what is left. That's it. Again, lowercase r is the radius of the small loop. Any remarks? Okay, part C, determine the induced EMF in the small loop. Well, by definition, the induced voltage in the small loop is going to be, in magnitude, is going to be equal to the rate of change of magnetic flux. Rate of change of magnetic flux. And we already said that the magnetic flux is this expression, but now the current is changing. So the magnetic flux now is some current, but it is changing. So you write it delta of whatever we had, pi r squared mu naught times n times current divided by the time interval delta t. So pi is constant, r squared is constant, mu naught is constant, n is constant. They can get out of the delta, and you're going to get pi r squared mu naught times n, and you're going to have delta I divided by delta t, which is given in the problem. It is 6 amperes per second. So this expression is 6 amperes per second. And everything else is known. You have to do the multiplication. This is one way to do it. Alternatively, you can do it with using other means. But this is one way. Okay, remarks and questions?
So the voltage induced is equal to the induced EMF.
Those are synonyms. Induced voltage and induced EMF are synonyms. EMF is outdated terminology, but it is still in use. And we use them interchangeably in this class pretty much. Okay, part D. So now they're asking the same question like part C, find the induced EMF, but now the loop is oriented not like this, but like, well, just imagine that it is perpendicular, so it is like this. Well, if the loop is oriented in such a way that the magnetic flux that goes through that loop is always zero, doesn't change, the induced EMF also is going to be zero. Because induced EMF is change of flux. The flux is fixed, doesn't change. It is zero, doesn't change. The rate of change is zero, and the induced voltage is zero in part D for this orientation.
Why is it that?
Because this angle, cosine of this angle, is going to be zero. The angle is going to be 90 degrees. The angle is the angle between the direction normal to the plane of the loop and the magnetic field created inside the solenoid. That angle is 90 degrees. Cosine of 90 degrees is zero. And this is why for part D you have zero induced voltage. And finally, they want you to figure out the self-induced EMF in the solenoid. And for this, well, we can use different ways of reasoning. But probably, so you can do it in different ways. Let me do it the pedestrian way. The self-induced EMF, the induced prime, to make it different from the other induced voltages that we analyzed, is going to be equal to the rate of change of magnetic flux that goes through the solenoid. Let's get rid of the minus signs using absolute value notations. And the magnetic flux through the solenoid is going to be equal to the number of turns of this solenoid, total number of turns of the solenoid, multiplied by the area of this solenoid A prime, cross-sectional area of the solenoid, the circular cross-sectional area A prime. So this gives you area multiplied by the magnetic field inside the solenoid. Again, there is a cosine of some angle, but this angle here is equal to 0, so the cosine is equal to 1, so I'm not going to write it. So this is all of it divided by time. Now here in this formula, A prime is equal to pi capital R squared, the radius of the solenoid cross section. So for, it is 0.05 meters. So it is pi times 0.05 squared. Capital N is 1.5 times 10 to the 4 number of terms in this formula. Of course, you still don't know the magnetic field B, so you have to figure it out. The magnetic field B inside the solenoid is what we said. It is mu naught times lowercase n times the current. So substitute that expression here, and you're going to get the rate of change of n a prime mu naught n current with time of delta t. And look, everything that is inside those brackets is constant except the current that is changing at the rate that they give. So everything that is constant can be taken out of the delta. So you're going to have n a prime mu naught times lowercase n, and only delta I divided by delta t. But this delta I divided by delta t is given, so everything else is also described. So this is going to be the self-induced EMF. Well, the expression in front of the self-induced EMF is also called inductance of the solenoid. So this expression is exactly inductance capital L of a solenoid, and we proved actually that inductance of a solenoid is given with expression like this, as one of the examples that we did. And we also proved that the self-induced EMF is inductance times the rate of change of current. So we could have answered that question by remembering the formula for self-inductance and the connection of self-inductance with induced voltage. But it is the same way. Okay, so this problem again is going to be given upon request. So you say, I want a version of the test with this problem, but you just have to make sure that you write well the solution with understanding, demonstrating understanding. Okay.
Yeah. Will the test that doesn't have this problem just have like a different type of problem?
It's going to have different types of problems, which in general are going to be less demanding. And here you practically go through the entire chapter 22. And you may get lost in the logic of going through it. So the other versions are going to be shorter, easier problems. But which problems exactly, we don't know. Okay, let's see questions and remarks about any problem from the practice test, from the homework assignments. And I thought that I emailed you a list of conceptual questions, but I was told that I didn't. So I'm going to email the conceptual questions from the 3 last chapters at the end of this class. Yeah.
I was just wondering if these formulas that you use are going to be on the formula sheet.
They should be on the practice test. If you look at the first page of the practice test, they are there. If some formula is needed and it is missing in the list of formulas, you have to ask, and I'll write it on the board.
Is it still okay for those of us that can't make it at 11 to come in
Yes,
person at 1?
yes. If you cannot make it at 11, you're welcome to come at 1 o'clock. Okay. Any questions? Anything?
Can we go over power factor?
So power factor is defined, power factor in RCL circuits is defined as a cosine of the phase angle between the current and the voltage in RCL circuits. And that power factor can be calculated as the ratio of resistance divided by impedance. The resistance is whatever is the resistance in the circuit, whatever is the value of the resistance of the resistor in the circuit, while impedance is defined as square root of R squared plus inductive reactance minus capacitive reactance squared, everything under the square root. So this formula is useful formula for, so power factor is a number between -1 and 1 because cosine has values between -1 and 1. Okay. Any other questions? Any remarks? Any homework or other problems?
Example number 19 from practice test.
Problem number 19 from the practice test. Okay, let's look at this problem. Problem number 19 from the practice test. So you have RCL circuit.
That is 18.
I'm looking at the wrong, I'm sorry. Okay, problem number 19. You have two wires with current in there. And they're asking you to figure out what is the value of the magnetic field created by those two currents at some specific point, which happens to be at the origin of the coordinate system. Well, the magnitude of magnetic field created by the first current, 50 amperes, is mu0 times the value of that current divided by 2 pi, the distance between the wire with this current and the point of interest. So call that distance R1, or the current I1, that distance is exactly 5 meters. R1 is given. Similarly, the magnitude of the current created, the magnitude of the magnetic field created by the other current, again, is similar expression. The value of the other current divided by 2 pi, the different distance, and that distance, the distance between the second current and the point of interest is 4 meters. Now, the magnetic fields B1 and B2 are vectors. They have to be added as vectors. And you have to use the second right-hand rule to figure out the direction of that vector. So the direction of the first magnetic field, the 50 amp current, you place the thumb in direction of the current, and the magnetic field lines are circles oriented like this. If you look from above, those are circles that are in counterclockwise directions. And the magnetic field at the point of interest is going to be tangent to that circle. In other words, it is going to be directed in negative y direction right here, this way, negative y direction, the first magnetic field. So if you look at xy axis, x-axis here, y-axis positive direction up. So the first magnetic field is going to be negative y direction, if you look at a different coordinate system. Now, the magnetic field from the second current, again, circles, and again, using the second right-hand rule, it is going to be a circle like this. And that direction of that magnetic field is tangent to that circle, which coincides with positive x direction. So the second magnetic field is in positive x direction like this. V2 is in positive x direction. So you have to add two perpendicular vectors. And using the rules for vector addition, right? Take one of the vectors, put it on the head of the second one, right? So here, 2 right here. The resulting vector is this. Call that resulting vector B total. And since you form a right triangle with hypotenuse B total, it follows that B total in magnitude is going to be equal to square root of B1 squared plus B2 squared. Let's see questions here. If no questions, other problems, other.
We do 18.
Problem number 18 from the practice set. So you have a generator with a given voltage provided by the generator, RMS value of that voltage, and RCL circuit with inductor, capacitor, and resistor, all of them connected in series. The first question is, what is the peak voltage? Yep. So the first question, what is the peak voltage? So you have to know the connection between amplitude and RMS. So amplitude of anything is equal to RMS multiplied by square root of 2. So they say that RMS value, they give you the RMS value. What is the amplitude? What is the peak? You say V naught is VRMS, which is given, multiplied by square root of 2. So the first question is answered. Second question, what is capacitive reactance? Well, those are just definitions. The capacitive reactance XC is 1 divided by 2 pi frequency times capacitance. What is inductive reactance? It is 2 pi frequency multiplied by the inductance of the inductor. Part B, find the impedance. part B, the impedance. Well, the impedance is by definition square root of resistance squared plus inductive minus capacitive reactance squared. So XL and XC are calculated. The resistance is given. So you have to do this arithmetic. Part C, what is the peak current, not RMS current? Well, current amplitude is voltage amplitude divided by impedance. And you know voltage amplitude from part A, you know impedance from part B, just divide them. D, what is the phase angle? Well, the tangent of the phase angle is equal to XL minus XC divided by the resistance. So from here, the angle itself is equal to inverse tangent of XL minus XC divided by the resistance. So that angle may come negative, may have negative value depending upon the values of inductive and capacitive reactance. You have to keep that algebraic sign. E, average power supplied to this circuit. So that average power can be calculated in multiple different ways. In class, we wrote 4 formulas for average power in RCL circuits. But one of those 4 formulas is current squared RMS value multiplied by resistance. So this is one of the 4 formulas or so. So the current is known, right? You have the amplitude, the RMS value of the current is the amplitude that you have from part C divided by square root of 2. And any of the other formulas is also going to give you exactly the same result. Part F. What are the peak value of the voltages across the inductor, resistor, and capacitor? So this is just Ohm's law of formula similar to Ohm's law. So the peak voltage across the inductor is going to be equal to the peak current, which is known from part C, multiplied by inductive reactance. Ohm's law slightly modified. In a similar manner, peak value of capacity of the voltage across the capacitor is going to be the current peak value multiplied by capacitive reactance, and peak value of the current, peak value of the voltage across the resistor is going to be in a similar way, current multiplied by resistance. And this is all of it. So again, this problem is making sure that you know what the terminology practically and definitions. And the definitions, of course, are given as formulas in the formula sheet.
On C, would it also work to do the peak voltage divided by resistance in that case? Because
Nope,
it would
it
not.
is not going to give you, no. So the current, you need, so you cannot, you unfortunately, if you had no capacitor and inductor, yes, that would work. But if you have capacitive and inductive reactance, you must have impedance instead of resistance in this Ohm's law type of formula. Other questions? No other questions? Well, if there are no other questions, let's continue with the material, and we have 10 minutes. We can use those 10 minutes to do many things. Right? So if you don't have other questions, let's continue with chapter 24, which is not going to be part of the midterm next week. So you have, we demonstrated that if you have a generator of AC voltage, this generator is going to emit a pattern of electric and magnetic fields, and this pattern of electric and magnetic fields is going to move away from the generator with the speed of light, and this is what we call electromagnetic wave. The pattern of electric and magnetic fields looks like this. The electric field oscillates with envelope given like this, while the magnetic field oscillates in a plane perpendicular to the plane of oscillation of the electric field. So it is going to oscillate like this. The electric and magnetic field vectors themselves are going to be vectors like this. So the continuous line is just the envelope of the vectors. The physical meaning is in the vectors themselves. So the red vectors are the magnetic field vectors, and the white vectors are electric field vectors. Yes. So now, this type of electromagnetic wave has select directions in space. Look, the electric field vector oscillates only up and down, up and down. It is a preferred direction for the electromagnetic wave that is drawn on the board. We say that this is the axis of polarization. The axis of polarization of this electromagnetic wave is the direction in which the electric field oscillates. So this is a polarized electromagnetic wave. Normal light sources like from fluorescent light sources or incandescent light sources, are not polarized light sources. This means that at some short time interval, the direction of polarization is like this. In next time interval, the direction of polarization is some completely different direction. So the oscillation of the electric field is, let's say, this way. A little bit later, completely different arbitrary direction of polarization. Still, the electric field vector is perpendicular to the direction of propagation of the electromagnetic wave. So if this is in state of C, I used V for the speed of propagation. The electric field vector is perpendicular for the velocity of the electromagnetic wave, and the magnetic field is also perpendicular to the velocity vector. And also electric and magnetic field are perpendicular to each other. So the three vectors, direction of propagation, electric field, and magnetic field form three perpendicular vectors, form a right-handed coordinate system, with electric field first, magnetic field second, and direction propagation third. Now, we said that most natural sources of light emit not polarized light. We, in other words, instead of a single direction of oscillation of the electric field, you have every single possible direction of oscillations happens there equally often, like this. Oscillations along the entire 360-degree angle circle. Well, there are artificial sources of light that are polarized. Lasers, for example, laser light is polarized, linearly polarized, and the light emitted by a laser oscillates in a pattern similar to the pattern that is shown on the board. If you have unpolarized light, like the light that comes from the fluorescent lights on the ceiling, there are materials which polarize unpolarized light. So there are materials like this filter, which incoming unpolarized light on the other side comes out with reduced intensity, reduced brightness, but polarized in one direction. And this is how sunglasses, polarized sunglasses use filters like this. So in those filters, there are plastic materials usually, in which long polymer molecules in the plastic are oriented in the manufacturing process in such a way that they arrange themselves, let's say this way, and usually this direction of arrangement is related with the direction of polarization of the light that goes through polarized filter. You're spending a lot of time in front of light sources that are almost completely 100% linearly polarized. And you can see those light sources that they're polarized just by taking this filter, placing it in front and rotating. So all LCD screens, including the screen on your cell phone, the light is practically 100% polarized, and you see that polarization. So when the axis of transmission of this filter coincides with the axis of polarization of the light emitted from the screen, you see that it is transparent, you see it very well. If they are perpendicular, you have complete absorption of the incoming light. You don't see anything behind the filter. So pass it around, look, the cell phones are exactly the same filter. So some cell phones, the polarization is only, so you have to, yeah, some cell phones, the polarization for different colors is different direction. So here you see that it changes the color for you. Because the direction of polarization for one color is different from the direction of polarization for other color. Okay, so with this, we have what, 1 more minute? 2 more minutes? Do you have questions that I can answer related with anything? Or not related to anything? Well, if you don't have questions, just play a little bit with this. I have another filter too. You can use that now. Let's see if your okay. Yeah, this is slowly changing the colors, but not. Yeah, let me try the other one. Let's try the cell phone. Look, it has some small change of the colors, but yes, that's
Oh, wow, look at that.
but you see it better on the big screen LCD display. Okay. So a test on Monday, please, if you can come at 11 o'clock, come at 11 o'clock if possible. Otherwise, come at 1 o'clock. And